Continuing with where we left off in the last video, in this video we'll find the variance of the random variable x that follows the exponential distribution. So to find the variance of the random variable x, this is equal to the expected value of the square of x minus the expected value of x squared. And in the last video we found that this value is just equal to 1 over lambda. So in the end, all we have to do is to evaluate the expected value of x squared, and then we will subtract that by 1 over lambda squared because we're squaring this entire expression. So now for the rest of this video, let's focus on this term. So for the expected value of x squared, in order to evaluate this, we just apply the definition of what an expected value is. So we have x squared multiplied by the probability density function dx. And then for the case of the exponential distribution, the probability density function is just equal to lambda multiplied by e to the power of negative lambda x. And then we can pull this lambda outside of the integral just to keep things simple. And so we have this x squared term multiplied by this e term. And in order to solve this, we'll have to use integration by parts. So the first thing we're going to do is to break out this entire expression into two separate components. There's the x squared and the e term. Now we will first find the antiderivative of this e term. So we have e to the power of negative lambda x divided by negative lambda, and then evaluate this from 0 to infinity, and then we will subtract this by by the integral from 0 to infinity of this expression. But now instead of taking the antiderivative, we'll take the derivative of x squared, so we get 2x. This is just the standard procedure for integration by parts, and so this is what we have. And then you see the two negative signs here, they all cancel out. And then in the end, you can see that for this term over here, when x hits infinity, when it tends all the way to infinity, you have this e to the power of negative infinity term, which is extremely small. It dominates over this infinity square term. So it's equal to 0 when x tends towards infinity. And then when we have 0 multiplied by 1 over negative lambda, because e to the power of 0 is just equal to 1, so this entire term is also equal to 0. And so we're left with this term over here. So we have 2, so we pull this 2 outside of the integral, and then we have x multiplied by negative lambda x, and then we also have this lambda term over here, and then I'm going to pull this lambda term outside of the integral, and then for this other lambda that we have outside of the integral, I'm going to put this back inside. And the reason why I'm not canceling these two out is because if, let's say, we rearrange this a bit, if we take a look at this integral over here, this is just the probability density function of the exponential distribution. And then this is multiplied by x, integrated from 0 to infinity. This entire term is just equal to the expected value of x, which we found is equal to 1 over lambda. So this entire expression is just equal to 2 over lambda times 1 over lambda. So we get 2 over lambda squared. And so this is the expected value of x squared. And so going back here, we can now substitute in the result that we just got. So we have 2 over lambda squared minus 1 over lambda squared, which just gives us 1 over lambda squared. And this is the variance of the exponential distribution.